Hey everyone, I'm Julia and I tutor GCSE and A-level chemistry, and today we're looking at ice tables. Ice tables are one of those things that sound extremely complicated, but in reality they're one of the easiest things to use. Once you've learned how to use them properly, they make equilibrium questions so simple. So let's get into it. Alright, so ICE stands for Initial, Change, Equilibrium. It's just a really neat way to organise your work. So initial is just what you start with. Change is what is gained or lost as the reaction shifts, and equilibrium is what you end up with. However, instead of using just ice, I like to add one more letter, which is the letter R. And R stands for the ratio of moles, which I'll explain further in our example. So let's try to use this method in a real question. So the first question is, in the reversible reaction below, nitrogen monoxide reacts with oxygen to form nitrogen dioxide. And the equation is 2NO plus O2 will form 2NO2. So then we're told that a 4 decimeter container initially contains 2 moles of NO and 1.5 moles of O2. We're also told that no NO2 is present initially. However, at equilibrium, 1.6 moles of NO2 has formed. Calculate the equilibrium constant Kc for the reaction at this temperature. Give your answer with an appropriate unit. So let's start off by writing out our equation. Okay, so now that we've got our equation written down, let's go ahead and draw our rice table. So let's quickly remind ourselves. R stands for the ratio of reactants. I stands for the initial concentration. C stands for the change in concentration. And E stands for the concentration at equilibrium. Alright, so now that we've got our table, all that we need to do to fill out our first row is look at the ratio of reactants compared to the ratio of products. And the way that we do this is just simply by looking at the big balancing numbers in front of each molecule. So for NO, that's supposed to be NO, not NO2. So rub that out. So in front of the NO, we've got a big 2, so we'll just place that 2 into this column. And I'm just going to go ahead and extend the table to make it slightly easier to follow. Okay, there we go, and then in front of the O2 we've just got a 1, as there's no number written there, so then we can assume that it's just a 1. So we'll place that into this column, and then we've got 2 NO2, so we'll pop that 2 into this column. So now let's go ahead and look back at the question and see how much of the table we can just fill out by simply using the information we're given in the question. So in the question we're told that a container initially contains 2 moles of NO2, so we can fill that in, and 1.5 moles of O2. We're also then told that at equilibrium, 1.6 moles of NO2 has formed, so we can pop that in underneath the NO2 column. And then lastly, we know that at the beginning of the reaction there's going to be no products, so we can simply put 0 in the initial concentration of NO2. Okay, so if we have a look, all of this was filled out simply using the information that was found in the question. We haven't started doing any workings out yet. So now what we want to do is fill out the rest of the table using the information given to us. So the easiest thing to fill out now will be the change in concentration of NO2. So we can clearly see that the NO2 goes from 0 moles to 1.6 moles, which is simply an addition of 1.6 moles. And since this is an increase of moles, we'll put a plus in front of the 1.6. So when calculating the change in concentration, it's crucial to check if the ratio of moles is the same in all the reactants and the products. So in this case, we've got 2 moles of NO2 as well as 2 moles of NO. However, we've got 1 mole of O2. So as a rule of thumb, the number of reactants is going to decrease during the reaction and the number of products is going to increase. Hence why we'll always put a minus in the change in concentration in front of the reactants and a plus in front of the change in concentration of the products. So now, since the NO2 and NO have the same molar ratio, if we gain 1.6 moles of NO2, then that means we'll lose 1.6 moles of NO. However, the O2 is slightly more complicated. Since the oxygen is in a 1:2 ratio with the NO, if we lose 1.6 moles of NO, that means we'll lose half the amount of O2. So that means we'll lose 1.6 moles divided by 2, which gives us 0.8 moles of O2. So we can write in 0.8 moles. Okay, so now that we found the change in concentration, all that's left is to calculate the concentration at equilibrium. And the way that's done is by doing the initial concentration minus the change in concentration. And essentially what that means is just the concentration of reactants left in the equation at equilibrium. So what we'll do is take the initial concentration of 2 moles of NO2 and take it away from 1.6 moles, which leaves us with 0.4 moles. Now we'll do the same thing with the O2, which is going to give us 1.5 moles take away 0.8 moles, which leaves us with 0.7 moles. Okay, so now that we found the concentration of all the molecules at equilibrium, all that's left to do is to ensure that they're all in the correct units. And since the unit's always going to be moles per decimeter cubed, we need to make sure that this is in decimeters cubed. So if we refer back to the question, we were told that a 4 decimeter cubed container was used. And since the container was 4 decimeters cubed, not 1, we need to divide all of our final answers by 4. So let's go ahead and do that. So 0.4 divided by 4 will give us an answer of 0.1 moles. Then 0.7 divided by 4 will give us an answer of 0.175 moles. And lastly, 1.6 divided by 4 will give us an answer of 0.4 moles. Okay, so now that we've got our concentrations at equilibrium, the last step is to write down the Kc equation. So Kc is equal to square bracket NO2 square bracket squared, since we've got 2 molecules of NO2 in the equation, divided by square bracket NO, since we've got again 2 moles of NO in the equation, which gives us a squared, and then square bracket O2. And we've only got 1 mole of this, so it's not squared. So now let's sub in our concentrations. So we've got 0.4 moles on the top, squared, divided by square bracket 0.1 moles of NO2 squared again, and that is times by 0.175 moles of O2. And that gives us a final answer of 91.428571. And rounding that up to 3 significant figures, Kc is equal to 91.4. And to figure out the units, we'll do something similar. So each unit is going to be moles per decimeter cubed. So we'll pop it into this equation instead of the concentrations. So we'll get moles per decimeter cubed on the top squared, divided by mole per decimeter cubed squared again on the bottom, times, there's always a little times here, again mole decimeter minus 3. And then to work this out, we've got moles per decimeter squared on the top and moles per decimeter squared on the bottom, so those can cancel out. And so what we're basically left with is 1 over moles per decimeter cubed. And another way to write this is simply by doing moles to the power of minus 1, since we flip it, and then decimeters, instead of the minus 3, we'll do a 3 since we flip the sign. So after all of that, Kc is equal to 91.4 moles to the minus 1 decimeters cubed. And boom, that's the final Kc value. So let's look at a quick summary just to solidify what we've learned today. So for the summary, the first thing that you want to do is write out the balanced equation on your page. Then what you want to do is use Rice tables with clear changes in concentration, and remember to use stoichiometry to show how the concentration of the reactants changes. Thirdly, what you need to do is convert equilibrium moles to concentrations by dividing by the volume, which in our case was 4 decimeters cubed. Fourthly, what you want to do is substitute your answers into the Kc expression and calculate Kc. Lastly, what you want to do is calculate your units and then add them onto your Kc value. And that's how you calculate Kc using a Rice table. Just follow the stoichiometry, convert to concentrations, plug in and check your units, and that's it. If you found this helpful, like, subscribe and comment below with any topics you want me to cover next. You can also check out my video on calculating Kp using partial pressures. You've got this.